Hello. Thank you for this wonderful turnout so early in the year. We're very lucky to also welcome to 2026 AstroSeminar series. Let's go. We're very lucky to start this year off with Duncan Lyster. Duncan, am I saying that right? Lyster. Duncan used to work here in the first year lab, but then he left us to go pursue an academic career at the University of Oxford. And today he's going to be talking about what he's been doing over the past 2.5 years.
Cool. Well, thank you so much for having me, and thank you so much for all showing up. I know it's like a bit of a weird time of year in the academic calendar, so it's great to have an audience. I was sort of counting up the people I knew and said they were going to come, and I was up to 3. So yeah, it's really nice to have a few more than that here. And yeah, really nice to be back here and seeing so many familiar faces. So yeah, keen to tell you about what I'm doing. So yeah, if you don't know me, I'm Duncan Lyster, and I'm a PhD student now at the University of Oxford. And I'm in my 3rd year of my PhD, which bizarrely, because it's the UK, means that there's a very good chance it's my final year of my PhD. I'm really gunning to finish by October this year, but we'll see. It's obviously a classic thing to extend by at least a few months. So I'm just getting some of this stuff wrapped up. And so what I'm presenting here are probably going to culminate in 2 papers, and then hopefully some work that I'll talk about at the end, which is still planned and just very early stage, which I'm hoping will become a 3rd paper and really the direction of the research that I'm going to go on to afterwards. So yeah, I'm going to be talking about 2 key things in the solar system. So all solar system planetary physics, and all looking at airless surfaces. So I'm aware that most of you guys probably are looking at a bigger picture than that. So I'll say if you have any questions at any point and you think I've just missed something, feel free to jump in at any point, and I'll do my best to answer your questions. But otherwise, yeah, I'll leave a bit of time at the end. So I'm going to be talking about the Lucy mission, which is a NASA mission visiting asteroids in the solar system. It's visited a couple of main belt asteroids already, and then it's going further out in the solar system. And what we can learn, and particularly what I've learned from my involvement in that mission, that can be applied to icy moons. And specifically, I'm going to be talking about Europa. So Europa is one of Jupiter's moons. It's a very exciting place to be looking. And it's a particularly good time to be looking at it at the moment, because there are 2 space missions currently on their way to Europa. And we're going to learn a huge amount about it when they arrive. But all in good time. So I'm going to start off with a little analogy. So if I can this to move on. Okay. So this is what it all boils down to. The first thing is how light scatters and how light interacts with the surface. And the second is how a surface holds on to heat. And the rotisserie chicken here is an ideal example of this, because it does the same thing as an asteroid or a moon in the sun, which is it has one side facing towards the heat source, and it rotates, and the hot side cools down gradually, and then it heats up again as it comes back into the sunlight. So everything I'm going to be talking about is to do with both of these properties. Now we've got a nice simple convex shape here of the disco ball with light going off in all directions. But in many cases, what we're dealing with are objects that have concave surfaces. So you might have an asteroid that has 2 lobes, and you've got a neck region between the 2 sides. And so light that scatters off one interacts with the other side, and so that region can actually become much warmer than its kind of surrounding area. Now the same on this chicken, you can see some of those crevices where heat could get trapped in a little kind of almost like a black body cavity. And so you get interesting physics going on in these spots, and it's quite hard to actually computationally accurately replicate what's going on those surfaces. So it's an active field of research. But yeah, jumping back to a slightly bigger picture, now little toy model of the solar system, and I'm going to be talking about asteroids, and there's a few different regions of asteroids in the solar system. So mostly at school, we learn about the 8 main planets and the main asteroid belt, which is between Mars and Jupiter. But there's a few more regions. So there's the Kuiper belt, which is out beyond the gas giants. And then beyond the Kuiper belt, there's the Oort cloud. So where the comets out there are so dispersed from each other, there's very little interaction. And so they're still in a spherical shape rather than having collapsed into a disk. Now, there's a couple of others. You have to excuse the slightly hectic animation here. It's the best I could find, and it's a little bit fast. But this is showing two families of asteroids that orbit with Jupiter in its orbit around the Sun. And so those are known as the Trojan asteroids, and they sit at the L4 and L5 Lagrange points. So the ones orbiting in front of Jupiter are known as the Trojans, and the ones behind are known as the Greeks. And the Lucy mission, which I'll be talking about, is going out to visit these asteroids. Now, I'll just show another little animation that shows that family. So in green, we've got the Trojans, and in pink, you can see it against the black background, is another family called the Hildas. And I just put them up there because they've got such a weird orbit. They're in a 3-to-2 resonance with Jupiter. And so they end up forming this kind of triangular shape as they orbit around the solar system. But the Trojans in particular, using Trojans here to mean Trojans and the Greeks, are thought to be very early remnants of the solar system. So still rich in volatiles like water ice and CO2, and maybe an indication of this idea that a lot of the water on the Earth came from a bombardment of comets late after its early formation. So the Earth, we know, is very dry when it was a lava world when it just formed, and all of the water, we think, came from comets. And so investigating these and understanding how they're formed, what their morphology is like, what their composition is like, is a really important piece of that puzzle. So that brings us to the Lucy mission. Now, this is it's named after the Lucy fossil, which was one of the earliest at the time it was the oldest upright standing human fossil that had ever been discovered. Discovered by a guy called Donald Johanson, who's going to come up a bit later. And the idea behind naming it, the press version is that the Lucy fossil was an early remnant of the human species, and the Trojan asteroids are an early remnant of the solar system, and so you're going to investigate these fossils. The version that I heard from the person who named the mission was that they both quite liked the song Lucy in the Sky with Diamonds. And that's actually what the fossil was named after as well, because it's playing on the dig site when they found the fossil. And obviously the name fits quite well with the space mission. But that's the spacecraft to scale, and you can see the size of those solar panels, absolutely huge, which they need to be because they're going out to Jupiter, much, much further from the Sun than the Earth. And it's very hard to get hold of radioisotope generators for spacecraft these days. So solar panels are the only option. They need to be really, really big. And the kind of the tour of the spacecraft looks a bit like this. In fact, I'm just see if my animation works. It has not worked in the past. Oh, there we go. Okay. So in blue, we've got the Lucy spacecraft. Green is Earth. The yellow one in the middle is the Sun. And so you can see it does an Earth gravity assist here. Then it goes past this asteroid, Donald Johanson. Remember the name from earlier. Out to the Trojans. And it's doing a few flybys of different asteroids in the vicinity of Jupiter. Then it's going to come back down past the Earth again, and it's going to get flung out to the other side, and it's going to go and investigate the Greeks. And so Donald Johanson, the flyby happened in April of this year. The preliminary Euripides, Lucas, and Eurus flybys are happening in 2027. And then Patroclus and Menicius, I don't know if any of you are specialists in Greek pronunciation, hopefully not, are going to happen much later. And so very long lifespan of mission and some really interesting targets. And the key thing about asteroids is that when you fly past one, we've only visited to date 19 asteroids in the solar system, and almost every single one has been a surprise in some way. And so the flyby of, let me just skip back a slide because it's not shown on that animation, but the flyby of Dinkinesh, which happened before the Donald Johanson encounter, was a big surprise. So that happened right at the start of my PhD, 2023. And ground-based observations looking at the light curve of the asteroid showed that it had a rotation period of about 50 hours, something on that ballpark. And so they're expecting to find an elongated object rotating so that when the long side was facing you, it would be bright, and when the short side was facing you, it would be dark. So that kind of makes sense. And then they got to the flyby, and it looked like this. So this is an animation from the LORRI camera, long-range imaging camera. And you can see that there's not just one body there, there's two. So the central asteroid is Dinkinesh. That's the name of the Lucy fossil in the native language of the country it was found in. And the satellite orbiting it is Selam. Now, the light curve of 50 hours actually came from the orbital period of that satellite around the main body. And the central body spins at about 4.3 hours rotation period, so a much, much faster rotation. But because it's rotationally nearly symmetrical, it doesn't contribute very much to the light curve. So a huge surprise and incredibly fortuitous alignment, because you don't know before you fly past an asteroid exactly how it's aligned. And you don't know, well, we didn't even know that there was going to be a satellite. So flying past it and actually getting both of those objects within the field of view, and even having an occultation, so the satellite passing behind the primary body, was really remarkable. And so this asteroid, kind of on its own, has been a really interesting case study in the process of Yorp, which I don't know if, are you familiar with that term already? So it's a radiative force that you get based on the object rotating and one surface of it heating up in the sun, and then as it re-radiates its heat back out into space, the actual photon momentum from that re-radiation applies a torque to the primary body, and it starts to spin, and it spins faster and faster and faster. And so the leading theory for how this satellite formed is that it was a Yorp shedding event, where that primary object, that spinning top kind of shape, is known colloquially as a Yorpoid, which is a word I didn't expect to add to my vocabulary. It spins faster and faster. You get a landslide on the primary body, and then it will briefly form a disk like Saturn's rings, and then that will reaccumulate into that secondary. And actually, in the case of Selam, the secondary here, you can see it's a bilobate shape. So there's two parts stuck together. And the idea is that they formed one at a time. So the first one formed, and then it migrated out through a process known as binary Yorp, which is a sort of subtle variation on the same process. And then that secondary body formed, migrated out, and then they met at very low speed so they could meet together without breaking up. So binary asteroids are really interesting. We've seen far more of them than anyone ever really expected. So I'll just talk a little bit about the background of those. So some binary asteroids you might be maybe familiar with. So the DART mission from a couple of years ago, double asteroid redirection test. It was a planetary defense mission from NASA to basically fly a spacecraft about the size of a fridge into the secondary body of this binary asteroid system and see how much they deflected it. So it's an interesting way to measure the mass of an asteroid, and an interesting test of basically how we might do this if there was an asteroid bound for Earth. There's Dinkinesh and Selam I just talked about. There's also quite a number of radar observations from the Arecibo Observatory. And actually, lots more binaries are still being discovered because there's so much Arecibo data that just hasn't been gone through, even though the telescope is no longer. We're still finding new binary pairs. But some of the best population studies actually come from double craters. So you can see the crater there on Mars, and you can tell this is a binary impact because rather than just two overlapping craters, one that formed earlier than the other, because of that straight line that divides the two sides. So that shows you that you can, there's really nice animated simulations of these. I should probably put one on my slides, but it shows this kind of splashing effect as all that rubble and the ejector comes up from the asteroid impact. And with a binary asteroid, you've got these two things moving at a few kilometers per second, and they impact within a split second of each other. And so the ejector forms this nice vertical sheet between the two impact points, and you end up with a very characteristic crater. And so by reverse engineering those craters, you can get a sense of the separation of those binaries, whether they were the same mass, like these two from Arecibo, or this kind of, turns out a 1-to-3 mass ratio is very common for binary asteroids. And so we're learning a lot about those asteroids. But one thing we don't really know is whether they have the same surface properties on those two asteroids. So whether they're formed through Yorp, or sometimes you might have a capture process where two asteroids, for whatever reason, drift close to each other. There's some momentum loss, and then they end up orbiting each other. There's a few different ways these could form, and so you can kind of confirm or reject those based on their composition. So if you see them and you say that, okay, Dinkinesh and Selam have exactly the same material composition, then that gives you a very good idea that they might have come from the same original body. So we also see these binary asteroids and interesting binary asteroid pairs. Now, I was lucky enough in April to go along to the US for a new flyby, which is the flyby of the asteroid Donald Johanson. And I couldn't resist putting in a few slides, a few pictures from the flyby, because there are a few good names there. So this is Donald Johanson himself, the guy that discovered the fossil. It was there for the flyby of the asteroid named after him. You might recognize Brian May on the left from Queen, astrophysicist in his own right. He'd just come from Coachella. and wanted to be there for the flyby. He was playing with Benson Boone, so I managed to buy him a pint. And then he was producing these stereoscopic images. So a 3D image, you show a different image to each eye. And it's really useful at the start of an asteroid flyby because those first images you get through look very flat and 2D. You'll see one of those in a second. And so when you're trying to get a sense of the shape of a thing, actually having that perspective view is quite a useful thing. It's also a cheeky way of getting in for the flyby, doing something useful and then getting out 2 days later, whereas the rest of us were there for a few weeks afterwards. But you can see the sort of the science operations room as that data first starts coming in. Very exciting time when you're getting these new images. So I was waiting for some kind of crazy two-body system or even more. There was a point where the terminal tracking camera, which basically works out what the spacecraft's looking at, it gives you what it thinks is going on before you get any images. And it was saying there were 5 bodies. And everyone was sort of scratching their heads thinking, what's going on here? I reckon actually it was probably counting craters or something along those lines, or something a bit weird going on. But we were there for those very first few images. And this is what we saw. So a weird sort of elongated shape. And you can see a few interesting things here. So straight away, the crater counting people were super interested in this because within the solar system, generally, objects that have lots of craters are very very old. So they've had a lot of time to accrue impacts, and those craters all overlap, and you can end up with a saturated surface where essentially every new crater erases craters that were there before. And younger surfaces are smoother. And so you can see this neck region is actually much smoother than the region on the right. And the first thought is, oh, maybe that's because of the illumination conditions. You know, if the sun's behind you, it's harder to see craters, and they're at different angles. But you can remove those effects, and it seems like that neck region is actually substantially younger than the region on the right. And so that's very interesting from a formation perspective. And what we think now happened is we don't know where the 2 bodies came from, whether they were Europoids as well or 2 independent asteroids, but that these 2 things were collided, and then gradually the neck between the 2 filled in through landslides, and you ended up with a smooth region. And every time there's an impact or a seismic event on the asteroid, you get little landslides, and so that rubble kind of fills in and erases any craters that were there already. Yeah.
Are those landslides, are they exclusively because of the Yorping process, or?
No, so you'll also get them potentially during close passages of larger gravitational bodies. So, for example, if an asteroid comes close to Earth and it changes its course, these things are such loosely consolidated kind of piles of stuff that any type of event like that can really shake up the surface and cause landslides. Also impacts. So if you, for example, had an impact on one side, you'd get a huge cloud of ejecta coming off, and some of that would resettle back onto the asteroid surface. And so that's also a big active field of research, is trying to understand how these things change over time. But yeah, I was there to look at the thermal side. And so the first thing to do was basically look at the data coming from the thermal instruments and try and work out if it made sense. So as soon as we saw the asteroid, I used Blender, it's a video games graphics thing that you can use to make 3D shapes, and made what used to be called a clay model of one of these asteroids. So in the early days, in fact, until quite recently, when they flew past a new body, they'd start off with a big ball of clay physically in their hands and squish it and squeeze it and put craters in, just so that people could talk about which hemisphere are we talking about here, which crater is this. And so just made one of those very quickly in Blender, put a few craters on it, and ran it through the thermal model to see what sort of surface temperatures we were going to be looking at. We knew the rotation period from the light curve beforehand. The problem with a flyby is it takes such a short period of time. The spacecraft's moving at more than 20 kilometers per second. And so from 1,000 kilometers away to 1,000 kilometers past it is really just a couple of minutes. And so you don't get very much of a sense of the rotation of the asteroid, particularly if it's a slow one like Donald Johanson. The rotation period, I've forgotten this, I won't quote it. It's much, much slower than Dinkinesh. But it's good to get a sense of whether those temperatures kind of make sense. And then if you notice thermal anomalies with your instruments, that might tell you that you've got a region that has different physical properties. So what we're looking for there is a physical property that's known as thermal inertia. And thermal inertia is a combination of thermal conductivity, density, porosity, and it's, I think, quite an intuitive thing if you see the right examples. So here's a couple of pictures I took on the trip. So Colorado has this crazy weather. One of the days while we were there, it was a day like this, like literally like 30 degrees outside, absolutely roasting. And we saw in the weather forecast it was going to snow the next day. I was like, are you joking? There's no way. But sure enough, about 9 o'clock, it started snowing. The temperature massively plummeted. And so we got snow falling. There's about a foot of snow, 30 centimetres of snow that fell overnight. And the next morning, it was this crazy scene where all of the footpaths and things, they hadn't been shoveled or salted or anything like that. But because the soil and the dirt that the footpath is made of is compacted, the snow that lands on it can't settle because the ground takes such a long time to cool down. Whereas the light, fluffy stuff, particularly the grass where there's insulation and so on, meant that the snow either side didn't melt. So you look around and you see these paths and you can actually spot regions of high thermal inertia. So those spots that have heated up in the day and they've stayed warm all night until the next day. And actually, even if you put your hand on the ground that next morning, you can still feel there was a bit of warmth to it. Now, the same effect you can see on the right-hand side. So you can see the gravel there and that pale line through it. Now, that's actually from France. And there was a similar thing, warm day. And then the next morning, it got a lot colder. It didn't snow, but the dew settled on the ground. And so everything got a little bit damp. But where that strip is, it's where there's a tile under the gravel. And so the same thing, that stayed very warm. And so the water didn't settle on the surface there. So you've got dry gravel next to wet gravel. Now, that's actually quite a good analogy for asteroids as well, because you see the way that thermal inertia on asteroids can affect where volatiles can sit. So this is particularly important on the moon. If you're looking for regions with water ice, which is a huge thing on the moon at the moment, still not even sure if it's really there at all. But if it is, it's probably in regions that are well shaded from the sun, and actually regions with higher thermal inertia, because it means the maximum temperature they reach is lower. So that water can still stay there embedded in the ground. So that's just a kind of an intuitive idea of thermal inertia. But the way that you can actually work out what it is on an asteroid is using a thermal model. Now, this is the first part of my sales pitch, and I'll get to the rest at the end of the at the end of the presentation. But what I've done for my PhD so far, so the first 2 years really were spent making this thermal model. So it's a Python-based thermal model, and thermophysical. So essentially, what you're dealing with is one of those 3D shapes, like you'd make in Blender, or like this very nice one made by the mission team for Dinkinesh. So that's done using a variety of techniques to actually produce a very accurate shape model. And the model looks at one of these facets on the shape model. It works out how much sunlight it receives in a day, then models the propagation of heat down through the surface throughout the day, and then the propagation of heat back up through the surface at night, and how that heat radiates away. And you can use that to produce a temperature map. So you can have a temperature map of the surface. But it's important to kind of take it one step further and actually forward model the observations from the spacecraft, because you end up with a situation where within your field of view, you might have different regions that are different temperatures, and even different regions that have completely different physical properties. So you might have one region with high thermal inertia and another region with low thermal inertia. And if that's all within one pixel, it can be quite hard to work out exactly what's going on. So what I did for the Dinkinesh flyby, and what I would like to carry on doing for the Donald Johanson flyby, but haven't got around to yet, is a bit of modelling of that actual flyby. Now, the situation we've got is a very fast rotating primary, so 3.74 hours, and a slow rotating secondary. Now, Selam is tidally locked to Dinkinesh, meaning it always faces one side towards Dinkinesh, whereas Dinkinesh rotates much faster. So there'd been some work done on this already, some kind of early thermophysical modelling by the mission team. And they had decided to just model the primary body. You know, it's much larger, so it should be the main contribution to the radiance received by the instrument. But I realized that because of this rotation rate and thermal inertia, actually the smaller body, even though it is, you know, substantially smaller in terms of area, because it rotates much more slowly, it has a lot longer to heat up in the sun. So it really bakes in the sun. And depending on the thermal inertia, it can get as much as 25 Kelvin hotter than Dinkinesh. Now that's a really significant difference because radiance scales with temperature to the fourth power. So a small difference in temperature can make a really big difference to the signal that you receive with your instrument. So I went through this process of forward modelling that instrument radiance. Now the instrument we're dealing with, the Lucy Thermal Emission Spectrometer, LTES, it's got quite a large field of view and it's a single pixel instrument. So you basically have one field of view and then you get this lovely thermal spectrum from it. So this shows the ground calibration reading, so you can see what the signal looks like. And we've got a low temperature target, 75 Kelvin, and a hotter target, 140. Dinkinesh is actually substantially hotter than either of those because it's only a bit more than 1 AU from the sun. But you can see here the kind of modelling approach. So the ring of dots there shows the field of view of the LTES instrument. And then basically what I've done is taken the geometry of the flyby, put that into the model, and then simulate the radiance coming off those instruments, or coming off those bodies. So you can see we've got a hot body and a slightly cooler body. And then you combine that into an integrated radiance profile, which looks something like this. And the first thing that I wanted to look at is whether just the shape of this peak could be replicated by including both bodies better than just by including one of the bodies. And if you're used to looking at this sort of data, you're probably thinking, okay, it's not the best quality. And that's true because the instrument really is designed for when it gets to the Trojan asteroids, those are much, much larger. So they're hundreds of kilometers instead of hundreds of kilometers. And so the instrument's not really designed to have deep space in the background. And so the signal to noise ratio isn't amazing. And there's this weird effect as well where the instrument basically measures the temperature difference between itself and the surface. So when it gets out to Jupiter's orbit, the temperature of the bodies it's looking at is much, much colder than the instrument. And so you actually get better signal to noise ratio from a cold body than you do from a warm body. But you can sort of see that we've got some key differences there. And I think I'm probably reaching the point with the investigation where I'm going to say it's very hard to constrain the thermal inertia of those two bodies independently. But it probably will be possible when we get to the Trojan asteroids. So you can see then fitting it actually in radiance space. So rather than just integrating that whole curve, fitting kind of individual observations, you can get in as deep as you want to it. But I think really I'd like to have some slightly better data. So I might wait until we've got that to carry on with this particular line. But it's important because the thermal inertia of asteroids really tells us something about their surface. So I can see a few quizzical looks there. You can see these kind of populations of thermal inertias, and you can see we've got kind of maybe some correlation between rotation period, diameter, and thermal inertia itself. But we're really interested in this York case because no one's ever measured the thermal inertia of two bodies that orbit each other. And so the idea is if we can show that the thermal inertia of those two bodies is similar, then we know that the surface properties and the surface effects are probably very similar between the two bodies. So a high thermal inertia in this case would mean a very dense, compacted surface, and a low thermal inertia probably means a very light and fluffy surface. So that's where I'm at with the asteroid investigation. But I promised I'd talk about Europa. And Europa is, in some ways, a very similar target, but there's a lot of kind of interesting stuff going on below the surface as well. So I'm going to jump across to talking about that before I get to my conclusions. So as I mentioned at the start, it's a very timely thing to be looking at because we've got two missions currently on their way to Europa to investigate it. So we've got the JUICE spacecraft at the top, so that's an ESA mission, and Europa Clipper, which is a NASA mission down at the bottom. Now, my understanding is that these were actually meant to be a joint mission, one spacecraft, shared between ESA and NASA, and they ended up falling out and being like, right, well, we're both going to go, I mean, maybe there's benefits to that. You get data from different things. So the ESA mission JUICE is focused more on Ganymede than Europa. It's going to perform a couple of flybys of Europa, and they've got quite complementary instruments, even to the point where their radar instruments, for example, the instrument on the NASA mission is called Reason, and the instrument on the ESA mission is called Rhine. So they've been trying to kind of tie those things together. Turns out radar in planetary science is quite a small field, so a lot of the scientists working on those two spacecraft are actually the same people. And so it's interesting because we're going to get there, suddenly get a huge amount of data compared to what we have from Galileo, which was the last spacecraft to visit the system and look at these moons. And so there's a lot of work that needs to be done to understand that data. And one thing I realized during the Don Johanson flyby is you kind of imagine with a mission like this, you spend so long preparing it, putting the spacecraft together, there's all clean rooms and the mission timelines are decades to get the thing off the ground. You'd think that by the time you got there, everyone would have their tools sharpened and ready to go as soon as the data arrives. And it's quite interesting to realize that it doesn't necessarily work like that. You get there and suddenly you're thinking, okay, well, it would be great to have a thermal model that can deal with this type of rotation. And you think, it turns out every thermal model that people are using, at least in the room, can only deal with a single spin state, so without having tumbling motion or anything like that. And the same thing applies to Europa. There are lots of challenges to doing modelling that can actually replicate the spacecraft data that haven't really been approached yet. So coming at it from a thermal modelling perspective, well, I'll talk about that in a second, but yeah, there's some interesting things to work on. So I thought I'd put this image up first because it's the only one I've managed to find that actually shows Europa and Jupiter from a spacecraft in the same shot. Can any of you actually see where, so there's two moons in this shot, Io and Europa. So the two closest into Jupiter. Can you see where they are? See a couple of pointers. Just up here on the right. So actually the brighter one there is Io, and just down and to the right is Europa. So really, really, really faint.
Where's the other one?
And I can't zoom in because we're right at the pixel limit of this image. It looks like really nice high-res image, but actually, as soon as you zoom in, it's very pixelated. So that's taken by Juno. I think really, really cool shot. I love these shots from Juno that show the poles of Jupiter. If you haven't had a look at them already, they're really eye candy.
Is there a shadow of one of them on Jupiter?
It's actually not. I think that's a weather system. Yeah, I thought exactly the same thing when I first looked at the image, but it doesn't quite line up. But yeah, so we've got those, and you get a sense of the scale as well. You know, these things really are tiny compared to Jupiter. There's a close-up if you want a better look at Europa. So Europa has this incredibly smooth surface for something in the solar system. If you look at any of the icy moons of Saturn or Jupiter, with the exception of maybe Enceladus and Titan, which has an atmosphere, you see they're completely covered in craters. They're pretty much at that saturation limit where every crater that is created on the surface erases other craters. Whereas Europa, you know, we can see craters here and there. There's a few, but I mean, it's far less cratered than our moon, for example. And so that tells us that this body has a surface that is in some way being resurfaced. So there's some type of erasure process going on. And the general consensus now is that what we've got here is an ocean world. So we've got an ice crust on the outside, almost completely water ice. And then below that surface is a global liquid water ocean. And there is some process, maybe like plate tectonics, maybe more like convection in the ice crust, that allows it to be resurfaced over time. Now that's really exciting from an astrobiology perspective because there's certain chemical reactions that happen much better and sometimes can only happen at all in the presence of radiation and UV light. And so if you're looking for conditions where life can evolve, you want complex chemistry and a heat source and, as we understand it, liquid water. And so you can have all of those things on Europa. You can have those complex chemicals coming to the surface, being modified and rearranged by the radiation and the UV environment, and then being drawn back down below the surface, where they can enter the ocean and lead to interesting chemistry. We know it's a salty water ocean because of magnetometer studies from previous missions. So you can detect the magnetic field of Europa, at least the way that it alters Jupiter's magnetic field. And so it's a really interesting place to look. The other thing that Europa has is a rocky core. And the rocky core interacting with the ocean is another one of those things where on Earth we have hydrothermal vents. And so you've got heat coming out from the surface into the ocean. And at least on Earth, we have life that can exist on hydrothermal vents that is completely independent of sunlight. It doesn't need sunlight at all to survive. And so a really interesting target to have a look at. Now, another interesting part with Europa is that there's actually very strong evidence that there's plumes that come out of the surface. So in some way, liquid water, we think, can erupt from the surface. Now, we know that happens on Enceladus, one of Saturn's moons, because it's been observed and photographed by the Cassini mission up close. With Europa, we've got some Hubble observations that strongly indicate it, but it hasn't actually been seen up close. So with a bit of luck, these two missions might come back with some really, well, not come back, but they might send back some really interesting information about those surface processes. And so there's a lot of questions about how water transport and heat transport happens in the crust of this moon. So this is a little schematic from a funding application I've just sent in, which gives you a little bit of a sense of the processes that we're looking at from a thermal perspective. So we've got the first thing, which I've talked about already, are those regions of altered physical properties. So if you've got a low albedo region that's absorbing a lot of sunlight, it'll heat up. Or if you've got a region of high thermal inertia, it might hold on to its daytime heat through the night. So it'll look like a hot spot, though it might look like a cold spot during the day. And these can be very confusing if you're looking for subsurface hot regions and you're trying to actually understand where the liquid water is. So they're the first thing to kind of be aware of. Then we've got a few kind of geological processes going on. So that first one, liquid water sill injection. So a sill in a geological perspective is where you have, on Earth at least, lava that comes up through fractures in rocks, and it will press between two layers and squeeze them apart, and you get a new injection of new rock in between layers of old rock. Now we think the same thing could be happening on Europa. We see indications of it with subglacial lakes on Earth, where high pressure water from below the surface sneaks up through fractures and it ends up embedding itself in this sill between two layers. It's called a sill. If you look at a cliff that has this type of feature, it looks like a window ledge, basically. So that's where the name comes from. And as those cool and freeze, if they end up near the surface, because of the latent heat, they'll actually produce quite a significant warm region. So this is one of the key things to be looking for with Europa Clipper. Another thing that we might see is impact-driven melting. Yeah, go ahead.
So, I'm sorry, wondering, you're comparing with like rock, and volcanoes and stuff. I guess the pressure is really high in the liquid, so the liquid wants to shoot up the same way that, is that what's called?
Yeah, so we've got, I mean, in terms of the hydrostatics, I guess, you've got, the reason we know that the surface must be water is because we've detected that magnetic field. It's too small to have a lava core. So we know there's a liquid, there's something liquid inside it. And so this means that the surface must be buoyant. It must be floating basically on top of that liquid ocean. And so we've got a buoyant surface, but as the thing that keeps it liquid is tidal heating. So you've got orbital resonances between Europa and Io and Ganymede. So 3 of those moons. And that means that Europa actually travels in quite a significant ellipse around Jupiter. And so as it gets closer to Jupiter and further away, it gets kind of stretched and squeezed. And that produces a significant amount of heating and probably all kinds of weird things going on with pressure, which are not, I mean, from a dynamics perspective, that's not my field. But my understanding is there's quite a big dialogue about what form that might take and how that stretching and squeezing works. If I go back to the previous slide, you can't actually see it too well in these shots, but you can see these kind of striations, these linear features along the surface, which are thought to be fractures caused by that kind of stretching and squeezing process, actually fracturing the ice. And yeah, so the idea is you get a fracture forming and the water will jet up to fill that fracture. Then we've got impact-driven melting. So an asteroid impacts the surface or a comet, and it melts the region just below the surface, and you might end up with liquid water near the surface for that reason. But then these two things are very different because in a sill, you might have ocean material actually very near the surface, whereas in the other case, you might have, if there's no transfer between the ocean and the surface, you might end up with something that looks like ocean water, but actually it's just ancient surface water that's just melted temporarily. And then we've got 2 other processes. So diapirism, which is like a convection that you get in solids, or potentially in kind of very slushy, partially frozen ice. And then convective upwellings, like we see in oceans on Earth. And so these are some of the key things to try and understand the differences between thermally. And just to kind of tie it back to the thermal modelling. So this is some work done by Sarah Howes, who's another PhD student in my group, using my model TEMPEST to interpret Galileo observations. So Galileo, I mentioned, is the last visitor to Europa. And it has some observations in the thermal infrared that allow us to, quite laboriously, I have to say, produce these maps of thermal inertia and albedo of the surface. And so you can see that those things vary substantially across the surface. She's got a great poster on it from a conference in the summer if you fancy having a look at that. I can put it up again later as well. And so you can see actually some of these spots really like very substantial deviations. We're going up to an albedo of about 0.8 there and down to 0.3. And there's a bit of noise in this, but most of that we think actually is real changes in the surface. And just visually looking at the surface of Europa, you can see there's a lot of different stuff going on there. And so what I've started doing and what I plan to continue doing now is combining this thermal modelling with some kind of geological models that predict where you've got these different heating effects. So you can see on the left, we've got subsurface heating only. So that's where I've basically said, okay, what if we've got these linear features along the surface? What if there's a heat source that follows that linear geographical feature? You think, okay, that sounds like a really easy thing to detect. You fly over the spacecraft, as you go over the line and go, oh, hot spot, and then it gets cold again. You do that a few more times, and you gradually build up this image that, okay, maybe we've got heating on these fractures. The other reason for doing that is that we actually see these features on Enceladus, one of Saturn's moons. These linear features, the fractures on the surface, are where the heat emanates from. And so that makes some intuitive sense. But then if you suddenly have a look at solar heating, the great thing about Saturn is it's at 9.5 AU, so it's so far from the sun that you can almost ignore solar heating. The endogenic heating, the heating from within, is so hot that you can see very clearly that the surface of Enceladus is much, much hotter than you'd expect at Saturn's orbit. The same is not quite true of Europa. It's half the distance of Saturn, pretty much. And so suddenly this solar heating, the kind of the passive heating from the sun, becomes really significant. And so when you fly over it, if you see something like this combined image on the right, it might be a lot less obvious that you're looking at something that's actually, particularly because it's aligned along these ridges as well. You can see that ridge, just because it's at a high latitude, so it's near one of the poles. Yeah, go ahead.
That's questions. How about the light reflected from Jupiter? Will that have an impact too?
Yeah, it does. And so that's ongoing work. It's quite tricky to model. There's a few different ways of doing it, but yeah, Jupiter shine is a very real thing on Enceladus. It contributes something like, at night time, it's by far the brightest source of light and of thermal infrared in the sky. So it's significant. And so it's another one of these things where, these missions are going to get there in just a few years. And we currently don't really have models that can deal with both of those effects. And so, yeah, you can see this, just from solar heating, you'll also see this linear feature because it's got a ridge that gets hot in the day. And as you fly over it, you might think, okay, this is a great sign of fracture heating, when actually it's not there at all. And of course, what we deal with in the real world is something that's a combination of the two. And so this is my kind of pitch that it's really important to do this thermal modelling and have an understanding of the passive environment, but also the active heating environment and how those two things combine. So second last slide. I was writing these conclusions just 10 minutes before the talk. So if you spot any typos, they're real. So yeah, the kind of takeaway from the Lucy mission is that you've got this interesting situation where just because of the different rotation rate of two bodies, you end up with one that's much hotter than the other. And that makes it very difficult to kind of interpret those observations. But then thinking about upcoming missions and particularly Europa, we're going to end up in a situation we've got the same thing. We've got different regions of different thermal inertias within the same field of view of the instruments. And there's instruments going to Europa that have multiple pixels, which is fantastic. But even those within the footprint will expect a huge range of different surface properties. And so my claim is that we need models that can understand those differences in order to be able to interpret those observations. Now, the other part of this pitch is that if you deal at all with thermal modelling or even scattered light phenomena, TEMPEST might be something that you could use. So there's a little pitch to the GitHub there. If you follow that, you'll find a YouTube summary and kind of how to get started with it. There's a few different groups using it now, and it's been fantastic to kind of watch it take off. One of the side missions that I went on was looking at the Lunar Trailblazer mission, which you might have heard about in the middle of last year, launched to go and orbit the moon with a lovely instrument made by one of the groups in Oxford. And then just before it was meant to do its lunar orbit injection burn, they lost contact with the spacecraft. And so it's now in an orbit around the sun. It's probably going to be destined for Earth again in about 5 years' time. And so the spacecraft went off and it disappeared. And we basically had these light curve observations from ground-based telescopes looking at the spacecraft. You could see it getting brighter and dimmer with this periodic rotation. And no one could work out which way around the spacecraft was. So we were trying to work out if there was going to be a point where the antenna was facing Earth, we could send a signal to it and get control of the spacecraft again. Spoiler is we couldn't work that out. But I did use TEMPEST to try and forward model that light curve from the rotation of the body. just because it's kind of, once you've got it up and running, it's an easy tool to use, and you can produce all kinds of different things with it. So yeah, that's me. I think we've got a few minutes for questions. So yeah, if there's anything you'd like to ask, then please go ahead.
We'll open it up to the room first.
One of the early models you did, I think the first time you showed us the use of TEMPEST, you got a temperature over time graph. I was wondering how sensitive things like that are to the initial conditions that you put in for your modeling.
Yeah, so it runs to equilibrium essentially. So the initial conditions are quite important for model like speed, like clock time. So the first step with TEMPEST is working out the illumination of each facet over one rotation. And then you take the average temperature from that rotation and you set all the facets to that temperature. But then one of the things I'm quite pleased with this model is I found a kind of a slightly hacky way to force convergence much quicker than other models, which is to break physics for the first few runs and just say that the top surface is equal in temperature to say that the deepest, so basically the model's divided into stacked layers and you run it until each rotation gives you the same temperature map as the previous one. And you can set the criteria for that. But the hack is to set the deep temperature to the T to the 4 mean of the surface temperature, which it's a slightly weird way of doing it, but it means it converges in like 5 rotations instead of like 100. So that's been really helpful. It means the model runs super fast, even just on a laptop. So yeah. Question.
Margaret?
For the beginning, you were talking about like contact binaries, and I guess with stars, you look at like the Roche lobe, but with these, how do you differentiate them from like an elongated object? Is it those landslides that you were talking about? Or?
Yeah, so I'll go back to the image that shows them. It's a good question, and I think it's not entirely settled. So, for example, looking at Itokawa, that wasn't really referred to as a contact binary early on, and it's only since we've seen a lot more of these objects. Like the prototypical one, I think, is 67P. So this is the comet that was visited by the Rosetta mission, and the analogy is that it looks like a rubber duck, and you can see that really clearly it's these two objects that are stuck together. And then you can see the same with Arakoth. That's a very visually and just intuitively you can see that that's two objects that somehow have ended up next to each other. And so then suddenly when you're seeing objects more like Donald Johanson and Tutatis, rather than thinking, oh, this looks like a splinter off a big collision or something, you start to think, oh, actually, maybe these did form from that initial contact of two separate bodies that then have had landslides form that neck region. One nice little thing that came out of the Donald Johanson flyby was they realized this neck region is such an important geological feature that it needs a name. So it's now called a column, which I think is Latin for neck. So that's a new recognized term in planetary science. But yeah, I think it's not entirely settled, and there's big questions about how common these things are as well. I saw someone at a conference just recently who was claiming that the majority of Kuiper belt objects are binary comets or binary asteroids, and saying that these things just form as a result of dynamic instabilities from the very early stage of the solar system. That binaries are the natural thing that you end up with. I don't know whether I think that's definitely kind of early days idea, but it's an interesting thought that they might be just way more common than we thought.
I might be misinterpreting the formation mechanism you're talking about when these two things come together. But what's the time scale of these two things orbiting each other? There's a landslide event and then they join.
Yeah, so that Yorp process.
Yeah. Years, decades?
It's a kind of an active thing. It's way more than that though. It's tens of thousands to millions of years. But that's still actually quite quick in the context of the solar system. Yeah. So the Yorp effect, it comes from the names of the people who came up with it, who are Yarkovsky, O'Keefe, Radzievsky, and P. Padak. And the first guy, Yarkovsky, initially came up with the Yarkovsky effect, which is a process, because the idea was that looking at the solar system, you can see these asteroids, they kind of seem to be in pretty regular orbits. And it's nice from a planetary defense perspective, because if you can work out where all the asteroids are, you can say, okay, great, well, they're not going to hit us in the next million years, so we should be fine. But the Yarkovsky effect means that actually, as a body rotates, Because the thing is, you've got radiation pressure from the sun working on these asteroids. So they end up sitting at an equilibrium point between their gravitational attraction and their orbital speed and that radiation pressure. But the only way to change something's distance from the sun is to make it go faster or slower in the direction that it's orbiting. And that Yarkovsky effect, like as you've got this thing rotating, say it's like orbiting the sun here. As it rotates, this side is heating up in the sun, and then it re-radiates all of its heat in the direction aligned with its motion. And so that applies that torque, and it means that actually these asteroids that we thought originally were quite stable in their positions can move quite substantially. They can deviate, and so you really do need to be constantly on the lookout because they can change in position. And so that York effect also happens. I mean, it's on the orders of kind of I think like centimeters per year, centimeters per second per year of radiation pressure effect. But it's still something that you have to consider if you're looking at the evolution of these things.
Duncan, can you hear me? Graham here. Duncan, can you hear me?
Yes.
Oh, Duncan, yeah. Just a quick question. The water's a certain level below the surface. I would assume that wouldn't be uniform. So some places it might be quite a large distance, other places might be quite shallow. I mean, it might be 100 kilometers in one place, 150 or more in another place. You think that will be quite important if they want to actually see how much water or do some analysis of the water below the surface? Because I would assume they would pick some place where it's closer to the surface.
Yeah, that's right. So it's a really interesting challenge is working out how thick that ice crust is. And we know from Enceladus that actually the poles are where the thinnest ice is on Enceladus. We think it's probably the same on Europa, but there are ideas that actually the thinnest ice might be near the equator. But you're right. I mean, the surface crust is probably at least tens of kilometers thick. So, a huge challenge. That's why neither of these missions is a lander. They're not trying to go down and actually sample that subsurface water. Not in this round of missions anyway. Maybe by the time I retire. But the thing that both of these missions have, so JUICE and Clipper, are ground penetrating radar. So this is the first time radar is going to the Jupiter system, and the hope is that radar will actually be able to give us a much better idea of the structure of this ice shell. And whether it's just fairly boring ice crust all the way down with no features within it until you get to the sea, or whether actually there are inclusions in these pockets and sills and things and convection that bring that ocean water much nearer to the surface, which would make it much more viable to sample it if that was the case. It's interesting with the radar as well.
Thank you.
No worries. I actually had a meeting with a radar guy this morning. So I had to stop on my way up here to pull in somewhere I get good internet. And the Clipper mission, which he's working on, the radar they've got on that is incredibly weak compared to the radar that's used, for example, in Antarctica to look at the glaciers there and the subsurface lakes. But because radar attenuation of ice is massively temperature dependent, actually the radar can penetrate much, much deeper on Europa than the equivalent radar. Like the equivalent radar on Earth might go down a couple of meters. But on Europa, even though it's a massively weaker radar because it's on a solar-powered spacecraft, it can still penetrate almost all. Basically, the idea is the radar people get annoyed because they keep being asked how deep it will go, and the answer is most of the way. If the ice crust is 10 kilometers thick, it'll go most of the way because the ocean is going to be where it gets warm and suddenly starts attenuating all the heat. If it's 50 kilometers thick, it'll still go most of the way because the ice is so cold that it'll penetrate fine. So it'll be very interesting to see what it looks like when we get there. Yeah.
Cool. Well, that brings us to 2:00 now. You're around for another couple hours.
Yeah.
If anyone has any other questions they'd like to ask, can we just quickly thank Duncan once again?
Sure. Thank you.
Is he coming?
The original